Welcome to my talk on the axiom of choice. Um, this was a talk. I've got to go back to the beginning. This is a talk I gave. When did I give this talk? In the fall for the local grad seminar at my university. So it's like a casual seminar we have on Fridays. It's just supposed to be like a 30-minute talk. Um, Not anything too crazy. This is probably not this is probably if much better first exposure to axiom of choice explainer videos on YouTube. I could even recommend some. Um, but anyways, we're gonna dive into some things in my opinions on the axiom of choice. Um, yeah, so starting off. Um, just to, I don't know, I feel like this example makes things make more sense with undecidability. Um, so there's these classic axioms that you'll find in Euclid's book, the axioms of Euclidean geometry, right? We can draw a straight line between any 2 points. Um, we can extend any straight line segment. We can draw a circle with any point as a center and a given radius, and all right angles are equal. But then there's number five, and I mean, it seems very different, right? It seems very long, winded, and the whole point of number five is basically to like define a notion of parallelism and say that like parallel lines never meet, essentially. So the interesting thing is, for centuries, people tried to prove that the fifth postulate follows from the other four. And there's even a YouTube channel, Extra History. They have a nice little video on the saga of this. And they talk about how there's like this one guy whose son was starting to like, he spent his whole life pursuing this, and his son started to think about it. And he like wrote some warning to his son about like, yeah, you'll waste your whole life away thinking about this problem or whatever. Um, and for good reason. It turns out that the fifth postulate is actually undecidable. So that means you can't prove that the fifth postulate holds. You can't prove that it's false either. And sure enough, like we can find geometries which satisfy the first four axioms and don't satisfy the fifth, and of course geometries which do. So you can take the fifth postulate, you can take that as an axiom in like ordinary Euclidean geometry in Rn. Will satisfy all of these things, but there's nowadays, we know about things like projective geometry, for example, um, in which this or hyperbolic geometry, in which this fifth axiom can fail in all sorts of ways, right? Like you can say, oh, all the points. So in projective geometry, all the lines that would have been parallel, or I mean, there are no parallel lines, right? So like every line meets in a point in exactly one point. But you could also have other geometries, like if you look at the geometries of like great circles on a sphere, like those intersect in more than one point. So it can fail in all sorts of different ways. So you've got three choices. You can accept the fifth postulate, you can deny the fifth postulate, or you can remain agnostic. Um, okay, so with that in mind, let's look at the postulates of mathematics, so to speak. Of course, there isn't just one foundation, but this is sort of the biggest one, most popular one we have is the set theoretic foundation. So these are axioms of set theory. Extensionality defines what it means for sets to be equal. Pair and union together essentially allow us to make unions of sets. We have the power set, allows us to create power sets, and the axiom of infinity, because just with those axioms, you can't actually prove that there is a set with infinitely many elements. I mean, you can show that you can inexhaustively produce new sets, but you can't collect them all into a new set unless you take this axiom. Well, I shouldn't say all, but an infinite number anyways. So now we come to the famous axiom of choice. And we're going to see some examples about, what does this have to do with choosing things? Because this is just sort of like a raw mathematical statement. So it says if you have any collection of sets, xi, there exists a function. So they're indexed by some capital I. Then there exists a function f from the indexing set into the union of all of them, such that f evaluated at I is in the ith set. So what this means in sort of normal language is that we're essentially picking an element from each one of these sets. So in 1928, of course, famously, Kurt Gödel proved that, well, he proved that if you believe that ZF is consistent, which everyone does, but no one can prove, then adding the axiom of choice won't break anything. You'll still have a consistent system of mathematics, right? So just like adding the fifth postulate, gives us regular Euclidean geometry, everything's all good. But it wasn't all the way until 1962, quite a bit later, that Paul Cohen developed this technique of forcing, which is now, very useful in the study of set theory. And he proved that the axiom of choice is independent of ZFC, which means you can create a model of set theory that satisfies all of the axioms, but which the axiom of choice does not hold. So just like how we can have, projective geometries, they satisfy the first four axioms of geometry, and the fifth does not. Yeah. So again, we're left with seemingly three choices. We could take the axiom of choice. We could take its negation. We could say the axiom of choice is definitively false, or we could remain agnostic about it. So what are the arguments for all of these? I mean, you've probably heard this is a controversial thing, right? Oh, I had some joke here. I guess I forgot about saying that that's it. That's all there is to say. Well, actually, I mean kind of, right? Because so I'm gonna give all of these arguments in a minute, but um, it's like, well, we've proved it's independent. So like who cares? Like take it if you want and don't if you don't. Like who cares, right? Well, well, here's the question. Because we also try to prove things using mathematics, not always, but we try and prove things about the real world. And so it seems like our axiomatic system could have implications for our theorems about the real world, right? So we wouldn't want to, yeah, we say we wouldn't want to introduce an axiom that could allow us to prove things about physics that don't actually correspond to the real world. Can we actually prove that anything does? I don't know. Let's get going back to um the talk. So of course you've probably all heard the Banach-Tarski paradox. Actually, that's the wrong name for it. I'm not even gonna see. I didn't even write it down. I just made a picture because I don't want to dwell on it that much. Um, First off, it's not a paradox. There's nothing paradoxical about it, unlike, say, Russell's paradox, creating a set of all sets that proved there was an inconsistency in Frege's theory of sets. It's a counterintuition. So I call it the Banach-Tarski counterintuition because that's all it is. It's a counterintuitive statement about the real numbers. I don't think that any serious mathematician holds this as a point against the axiom of choice. And if they do, then they're a very, very silly person. Because just because you don't like a theorem doesn't mean that, oh, I need to change the foundations of mathematics to avoid this theorem. Well, mind you, I mean, sometimes we do. That's the freedom of choice that we have is to work in the axiomatic system you want to. But with Banach-Tarski, I mean, first off, oh yeah, it's weird. I can rearrange these shapes in the real numbers. But here's the thing: if you drop the axiom of choice, it's not like Banach-Tarski becomes false, right? If you ignore the axiom of choice, it's just you can't prove that it's true. But the potential of that fact doesn't go away. And the other thing too is yeah, I mean, we built the real numbers in Euclidean space in the image of our physical world, right? But there are plenty of instances where it does not line up with our physical world. It's a very useful model for understanding physical things in our physical world, but it's just different. At the end of the day, it's just a different thing. And there's going to be places where it disagrees with the real world intuition that originally inspired those definitions. So yeah, this means absolutely nothing to me, one way or the other, when it comes to the axiom of choice. Okay, so let's get into some interesting examples here. So this will be here we'll see an example of why we call it the axiom of choice, you know. So here's our regular definition of continuity of a function on the reals, right? Classic definition. Um, Here's a theorem. It's a very, very useful tool. I'm sure you used it plenty in your first analysis class. It's continuous at a point A if and only if every sequence of points that converges to A, the sequence of the images of those points under F converges to F at A. Right? So one direction, you don't need choice at all. I'll leave that for the reader. However, if we look at the proof in the other direction, suppose F is not continuous at A, then notice this very interesting sentence here. For each K and N, we can choose X sub K in the 1 over K ball around A such that blah, 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 and then here's the rest of the proof, right? So this is the very sneaky thing where people, apparently when the axiom of choice, was first a thing, some of the loudest proponents or some of the loudest detractors who are against it were actually using axiom of choice in their work and they didn't even realize. It's because this subtle misdirection that happens when we use natural language to write this proof, right? What are we saying, right? Then for each k in n, we can choose x sub k in the ball of radius 1 over k. What are we saying when we're saying that? Well, we're saying that we have this collection of sets, the balls of radius 1 over k, that are indexed by the natural numbers. And we have a function. So think back to our definition of what choice meant. We have a function from the natural numbers into the union of all of these epsilon balls such that the function applied to k picks out an element in the epsilon ball 1 over k, right? So that's exactly the axiom of choice. Actually, we can technically get away with a weaker version of the axiom of choice because our indexing set is countable. So if you always assume your indexing set is countable, that's called the axiom of countable choice. Yeah. So we don't need full choice for this. We can take a weaker version and still get our nice theorems and analysis. Okay, well, one of the other big ones you've probably heard of is the impact on measure theory, right? We've got all of these subsets of the real line, like intervals and things like this. We would like to assign some sort of size to each of these sets. And that's the idea behind a measure. We just want to assign a number that to each subset of the real numbers that we think of as being a size. And there's a couple of things we would like this to satisfy, right? We want, if I have the line from 3 to 5, that should have length 2, right? So it should satisfy these intuitive things, not just on the closed intervals, but open and half open. The empty set should have measure 0. the entire real line should be infinite. It's an infinitely long line. If you take the disjoint union of two sets, or in fact, countably many sets, then you should just be able to add it together, right? If you have two separate line segments, the total length of the whole thing is just the sum of the individual lengths. Seems reasonable. You should have translation invariance. So if you have some set and you just move it over a bit, that shouldn't change the length. Seems reasonable. But so we want to know if we can come up with such a function defined on the entire power set of the real numbers. Famously, no, though, right? So we're going to define an equivalence relation on the real numbers so that two real numbers are related if and only if their difference is rational. Now, here again, seems very, you realize you're doing nothing significant going beyond like normal axioms. If you just say this in ordinary language, oh, we'll just choose a set X of representatives. So again, um, we are implementing choice, non-countable choice here, by the way, though, because this set has to be uncountable. So we choose a set of representatives. We note that X is the union of all of these. So of course, X plus Q, I mean, that's the set of all sums of things in X, and you add Q to it. So there's two possibilities, right? X could have measure 0, but in that case, since these are representatives for distinct classes, we have the real numbers is a disjoint union of all the X plus Qs. And so that's just the size of all the X plus Qs, but by translation invariant, we're just adding up a bunch of zeros. So then all of the real numbers has to have measure 0. But that's impossible, right? We said we want that to be infinite. Otherwise, there has to be some interval that we can intersect X with so that the measure of that intersection has measure greater than 0, right? Because eventually, right, if X has measure greater than 0, like eventually as this interval goes to infinity, then the measures, the measure of the set X intersect those intervals, that eventually has to hit a positive number, because the only other alternative is that X has positive measure. So, well, for this next one, I mean, it's probably better than me explaining it. Just sit down and do the set theoretic calculation. Like, just let X be in this union, and you can see that it's in this, it's a subset of this closed interval, right? So yeah, just pause and like do that computation. Oh, why is I didn't write out the last part of the proof. Why that's a problem. Uh, the point is, I believe the point is that, um, oh, what is the point? I forgot the contra. I didn't. So this is what happens when you give a talk based on slides you haven't looked at for several months, and you stupidly didn't write all the details down. Let's say we have an interval. It's got to be greater than 0. X is contained in that whole thing. Oh yes, okay, of course. So this would hmm, no. I don't see it. Okay, well, I'm not going to waste time here. For whatever reason, I don't see it, but we can derive a contradiction. Oh, now it's bugging me. Why do I put myself on the spot like this? Hmm. No, I don't see what I was supposed to contradict. Oh well, I'm gonna see it as soon as I stop recording. Um, yeah. So the thing is, the takeaway, much love the very last part of the proof, is that you can't have all of these things at once. And so people do study other things, right? So the typical thing we do is we just say, okay, um, there are some sets we will not be able to assign a size to. Some subsets of the real numbers we won't be able to assign a size to. And that gives you and you build a measure that satisfies the rest of the things called the Lebesgue measure. But also we can play around with dropping these any one of these other axioms. People do it, and there's interesting things to say about that. Um, yeah. So I already said that. Yeah. So yeah, again, yeah, like I said, um, really we used a stronger version of choice there, countable choice. We wouldn't run into this problem. But okay, so you might be thinking so far, oh well, maybe just countable choice, and that's a happy medium. But there are theorems like the Hahn-Banach theorem and the and Tikhonov's theorem that do well, I don't know. I'm not. I don't work in quantum mechanics. I don't know much about stochastic calculus, but what I do know is that those theorems come up. I've seen them come up in what little reading I've done on these topics, and they're quite essential. And like quantum mechanics that's a very real world thing. We're doing real world experiments with that. Stochastic calculus. I mean, that's our financial markets. So that seems to have implications for the real world. What does choice mean then? Does it mean something in the real world? Um, I don't think was I going to cover Han Banach? Well, anyways, you can read the statement if you want. But yeah, so I guess I just put it here for reference. Oh, yeah, also, yeah, functional analysis. It's a super important tool there, which is, I mean, the reason why it's important for quantum mechanics. But then again, oh yes, yeah, that's why I put this comment down here. Um, we also only, I think, in quantum mechanics, only work with separable Hilbert spaces, and so maybe we don't need full Hahn-Banach. I don't know. I don't know. Maybe a physicist in the comments can tell me their opinion. Right. And I mean, Tikhonov's theorem, a product of compact spaces is compact. Super useful. Super useful. Um, so here's a random quote I found from someone on Stack Exchange when I was preparing this. So presumably they know more about me on these topics. So without full axiom of choice, you don't have Hahn-Banach in function analysis, and a huge part of function analysis becomes invalid for PDE theory in particular. Tikhonov's theorem in topology is the basis of Banach allow glue. I forget how to say it. It's been a while since I took a functional course, which is the foundation of the theory of weak solutions, which then leads to elliptic regularity Hodge theory, etc. And Tikhonov is also responsible for the Kolmogorov extension theorem, which is the foundation for stochastic processes. So, okay, that essentially what I said, but I ripped it off from some uncited, possibly more trustworthy source. I don't know. Um, um, and in my own work, it has impact, right? I mean, I work with infinite dimensional stuff all the time, and the axiom of choice is equivalent to the statement that every vector space has a basis. Of course, you're used to thinking as every vector space having a basis, because that's how you were raised to think. But what right do you have to believe that? Now, here's the thing. Here's the thing. Actually, I should say this right now. People sometimes when there's discussions about the axiom of choice, people will say something. I'll make a snide remark like, "Oh, well, have fun with vector spaces that don't have a basis and blah blah blah." But here's the thing. There's a lot of cases where, like if you drop choice, that doesn't mean that suddenly no vector space has a basis anymore. Like finite dimensional vector spaces all have one by definition. And you can still like there's certain infinite dimensional vector spaces where you can still prove that it has a basis without choice. It's not, you don't necessarily need it in every instance, but it's just the guarantee that every vector space has a basis. So here's the thing. You could still go about, you could drop the axiom of choice, and literally every theorem that about vector spaces that uses bases, you can just say, suppose V is a vector spaces, a vector space that has a basis. That's all you need. You add one sentence in front of all of these theorems, and now they're still true theorems. So actually, you can still do a lot of interesting mathematics dropping the axiom of choice. It's not like this kills bases in general. Like same thing through Zorn's lemma with maximal ideals. It's like, yeah, the a lot of theorems, like we have a lot of theorems that are just, they're statements about having maximal ideals. But all you need to do if you want to drop Zorn's lemma is you just say, well, suppose I have a ring that has a maximal ideal. And a lot of rings in practice that we use, like in number theory or something, you can prove those have a maximal ideal without Zorn's lemma. So, anyways, that's my piece on that. Yeah. Oh, here's a freaky one though. The algebraic closure of the p-adic numbers is isomorphic as a field to the complex numbers, but only if you believe in the axiom of choice. Oh yeah, right. The point of the slide is these are all things that are very relevant to my research. I like come up on a daily basis. In fact, actually, there's some so okay, you can probably tell my leanings so far. Seems maybe I'm leaning against the axiom of choice. But um oh wow, I've been spiking my volume. I'm a loud talker. Um but there's um there's also a lot of problems if we take the denial of the axiom of choice. So if we say that if we believe in the negation of the axiom of choice, then there exists a vector space that has two bases which have different cardinalities. Um, yeah, that is a horrible statement. That is awful. There exists, you can also say that there exists a set A, such that for all subsets B of A, B is not countably infinite. Wait, I must be missing a sentence. Why is that a problem? It must be an infinite set. I should have said there exists an infinite set. I think that's the issue. Yeah. Um, Also, if you take the negation of choice, R can be a countable union of countable sets, but still uncountable, right? So this famous theorem, countable unions of countable sets are countable, but only if you believe in the countable axiom of choice. But okay, again, you look on Reddit and you see that, oh, there's these people and they're like, oh, well, if you take the negation of choice, like, I want my vector spaces to have like, look at all of these like absolutely terrible theorems that happen. And it's like, yeah, that's true. That will happen if you take the negation of the axiom of choice, but you don't have to. Right? The middle way is just being agnostic about the axiom of choice. You don't commit to it or its negation, and you just go about doing mathematics without either. And then you don't like there's terrible things either way, whether you believe in choice or the opposite of choice. So like sort of seems like just remain agnostic. Mhm. But here's my actual stance. Here's my actual opinion. Which is somewhat blasphemous because I mean I use choice every day. I use law of excluded middle every day. But here's what I think the real problem with the axiom of choice is. So I mentioned before, there's all these things, all these theorems, whether you like them or not like them. I mean, one argument that is okay is like, oh, I want to do interesting mathematics, and the math that interests me is the axiom of choice, so take it. Okay, I mean that's a valid argument. But most of the time, I don't really buy these arguments about, oh, I like these things, I like not, or I don't. But where I think there is a good argument for this is the law of excluded middle. So this is a statement that for all statements P, either P or not P. So you can always conclude either P is true or P is false. This is the same thing as saying is the double negation is equivalent to the original statement. And it turns out that the axiom of choice implies the law of excluded middle. And so my contention actually is not so much with the axiom of choice, it's with the law of excluded middle. But if you believe choice, you have to believe the law of excluded middle. Um, and why do I have what's the issue with law of excluded middle? Again, I'm saying this as someone who uses it every day, right? Um, the point is that the law of excluded middle is non-constructive. So what that means is having the law of excluded middle allows you to prove the existence of something without explicitly constructing it. So, for example, the game Chomp, I'll let you, I think in the talk I explained it on the whiteboard, but I'll let you look it up afterwards. It's a two-player game, and the point is, the thing about Chomp, so it's set up that like at the end, like if you lose the game, you die. You eat this poison piece of chocolate, right? So if you had to play this game in the real world, you were in some sick prison or something that made you play this against another prisoner or whatever. You would have to you would want to know if there was a winning strategy. Like if you're given the choice of do you want to be player one or player two? Like, do you go first or second? And you want to know, do you have a winning strategy? You want to know yes, and you want to know which one it is. The thing is, you can prove in Chomp that player one always has a winning strategy. The issue is it's non-constructive, which means even if you knew, so Chomp is played on a rectangular board, N by M. And the thing is, even if you knew the winning strategy for all boards of size N times M, for all N and M, as soon as you make one of those, like one row or column larger, it tells you you have absolutely no idea. It tells you absolutely nothing about how to continue playing the game on a bigger board. So now you could still say, well, at least you know that player one does have a winning strategy, so you should take player one, I guess. But it doesn't really tell you, right? So it's not really so useful. Certainly not as useful as having like the algorithm being given the algorithm to win this game, right? It's like if I told you that I've buried $1 million just for you in a suitcase somewhere on planet Earth. That's not very good information, right? That's not very useful because you can spend your whole life searching and never find it. I mean, it's effectively useless, right? It's essentially isomorphic to that not being the case at all, right? Um, so so this is my point for this. And so certainly when the axiom of choice comes up in say PDEs, like it helps you say, oh, there's a solution to this PDE, and that can be useful. I mean, I'm not saying it isn't useful at all, but if it doesn't tell you anything about what that solution looks like, it's also in some sense not very helpful, right? So this is my contention is essentially, proofs that don't rely on the law of excluded middle are better because they give you an explicit way on how to solve the problem, not just that it can be solved. And so this is, I think, the real reason to have a bone to pick with the axiom of choice and to maybe be more careful about the axiom of choice and the law of excluded middle in your math and think about when you're using it versus when you're not. Um, oh yeah, I wrote this weird thing down. Countable choice is constructively valid. I don't think that this is strictly speaking true, actually. But so if you take the literal definition as constructive mathematics, just does not believe in the axiom of choice at all. Strictly speaking, I don't think this is true. But because we still believe in sort of, but the constructive philosophy is still about that we allow computable things. And so countable things are still sort of like computable. You can still have a computer, have it implement some program and run for, maybe an unspecified amount of time, but it's still going to like it'll perform these discrete computations, possibly in an unbounded way, but it can still keep doing this computation, which may or may not halt, right? So we still, my vague understanding of this statement, it's more of a philosophical one that yeah, people who sort of believe in the constructive mathematics philosophy are willing to accept countable choice, um, so that we can still sort of do these computational things in a possibly unbounded way. Um, Yeah, I guess these are just some other honorable mentions. So Brouwer's fixed point theorem, right, says if you have a continuous map from a ball to itself, um, it'll always have a fixed point. So one interpretation of this is like well, there's the Hairy ball theorem, I guess, is another way to put this, right? You know, well, okay, so Brouwer's fixed point theorem, I guess that's more used, fixed point theorems are used for like solutions of PDEs, right? So these sorts of theorems, they tell you, oh yeah, there's a fixed point. So you can use that to say, oh yeah, there's a solution. Tells you absolutely nothing about where that solution is or what it looks like. And the last one is the automorphism group of the complex numbers. So the automorphism group of the complex numbers, it's definitely got two elements in it as a field, I should say, the field automorphisms. You've got the identity, you've got the complex conjugation, and those are both continuous with respect to the usual topology on C. But it turns out that this is more for interest's sake than an argument either way. But it turns out that if you believe in the axiom of choice, there's uncountably many automorphisms, other automorphisms. Oh, well, so uncountably many in total, yeah. Um, But the thing is, you can't say what any of them are. So we know that there's identity, we know there's complex conjugation, but because the axiom of choice is inherently non-constructive, it guarantees you, okay, uncountably many automorphisms, but you can't write down a single one. Like you can't even write down the formula that you would use to potentially compute this. Like, it's impossible. You can do certain interesting things where you can sort of like locally say like you can take some subfield of C and you can take an automorphism of that subfield and you can extend it. And there's really wacky things you can do about like crazy extending, like crazy that do weird things with the real line. I don't remember how it all goes. But yeah, you still can't write down any of these things in full. So I don't know. That's spooky. But to summarize, right, in terms of pure logic, again, this whole talk was just useless rambling, um, because we've proved it's independent. So take the logically speaking, believe in it or don't. It doesn't really matter. There's things that suck about the axiom of choice, right? Non-constructibility, I think, for me is the main thing. But it also makes certain things possible, like the research I do on a daily basis. The opposite of choice also sucks. Probably worse. Probably worse. I think it sucks worse. Some of those theorems, but that is a purely vibes-based perspective. Some of those theorems seem worse. And finally, does it matter for the real world? I don't know. Our real world math is based off of this, but at the same time, it's non-constructive. So any facts, any of the math we have that applies to the real world, any facts about that mathematics that comes from choice is inherently non-constructive. And so, like, those things should not ever actually occur in the real world. So does it have an impact? I still don't know. I feel like maybe not. I feel like it can't, but I have no idea. So again, we're left with this slide. And I think that's it for the talk. Drop some questions, comments, and concerns in the comments, and I'll see you soon.